I'd like to welcome each and every one of you to today's Sustainable Energy Collaborative as we continue to learn more about the complex issues facing our utility and energy world. On October 7th, 2008, the Commission opened the Sustainable Energy Resources docket number 08-144U, for the stated purpose that the purpose of the docket is to explore the expanded development of sustainable energy resources within the state of Arkansas, building upon the efforts previously undertaken by the Commission to develop and implement energy efficiency programs in the state under the broad authority under the Energy Conservation Endorsement Act of 1977. The orders opening the docket stated that the end product of the inquiry is to develop a sustainable energy resources action guide for the Commission and Arkansas utilities in promoting sustainable energy resources. In this docket, the Commission has received numerous filings from the parties and has heard from a number of national experts on issues facing the electric and natural gas industry. Today, we continue to learn from national experts with a presentation from Mr. Hank Courtright on the various options available of how to address CO2 emissions. The Commission would like to thank Mr. Hugh McDonald for recommending today's speaker to the Commission. Today's topic is very timely for the utility industry, considering that both the EPA and Congress are working on proposals on how to address the very challenging issues associated with reducing CO2 emissions while having a carbon-based economy. Mr. Hank Courtright serves as Senior Vice President of Members and External Relations at the Electric Power Research Institute, known as EPRI, which is located in Palo Alto, California. He is responsible for Member and External Relations of EPRI's Energy Technology Assessment Center. He has previously served as EPRI's Vice President for Environmental Sciences Research, as Vice President of EPRI's Generation, overseeing research on fossil, hydro, and renewable generation, and as Technical Director on Energy Efficiency Programs. Mr. Courtright has over 30 years experience in the electric utilities industry with EPRI and the Pennsylvania Power and Light Company, known as PPL. He has a Bachelor's in Science and Mechanical Engineering from Pennsylvania State University and a Master's in Business Administration from Lehigh University. He is licensed professional engineer in both California and Pennsylvania. So if we could all give a big Arkansas welcome to Mr. Hank Courtright.
Thank you, Chairman Susky, the commissioners, Honorable Commissioner Reeves, and Dean Rutherford. I appreciate being here. It's a real honor to be here. I had the time, took about 2.5 hours and walked through the Clinton Presidential Library, which is a wonderful experience. So that was an added benefit of coming here and enjoying the time here in Little Rock. What I want to do is to provide to you a view of a pathway forward that we've been working with many people around the electric utility industry, government, others, including international organizations, and how to reduce the carbon footprint for the electric utility industry in the United States. Now, the work we've done is, and showing here is for the U.S., but we've done similar work for other countries around the world. For those of you who may not know EPRI, we are a nonprofit, independent scientific and technical research organization. We have offices in Palo Alto, Charlotte, and Knoxville, but we do work around the world, and we are involved in research on scientific and technical issues in 40 different countries, from Europe to South Africa, South America, Asia, Australia, and the United States and Canada. So we bring all that wealth together, working on a collaborative basis to look at these issues. Now, I mentioned this as a pathway going forward, but just like any other roadmap, if you want to go from one point to the other, there's always different roads you can take, depending on what you want to see, the view, and what you're interested in. One of the things that we've done in picking the pathway that we have is try to look at not on how only to reduce the CO2 footprint of the electric sector, but how do we keep electricity affordable and reliable at the same time. So those are some of the signposts that we're looking on as we go in this pathway. There's two key areas, two key challenges I'll be talking about today quite a bit. One is how to reduce the CO2 footprint, and basically the word decarbonize I'll be using quite a bit, the electricity sector, and then, like I said, providing reliable, affordable, and environmentally sensitive electricity. And the second challenge is making it technically feasible with a full portfolio of options of how we can do this. But I want to stress one thing, and you'll see this as we go through here, that where we get to in the year 2050 will depend quite a bit on the decisions we make in the next 10 years. So 10 years will lead to a path, we think, of 40 years of electricity supply. The one challenge that we have here, this is basically the CO2 challenge, where the U.S. is right now in terms of CO2 emissions. In 2005, that's the benchmark used in most legislation. And it drops by 83% out to 2050. Now, this is the same basic target used in the Waxman-Markey bills and the Kerry-Lieberman bill, and it's pretty much become kind of an accepted position in terms of CO2 reductions going forward. And this is for the entire U.S. economy, and you can see how much the electric sector is about a third of the total U.S. economy in terms of emissions. The other challenge we're looking at is keeping electricity affordable. Now, this is the price of electricity, inflation adjusted, for the last 40 years, going back, actually even further back than almost 50 years. But if you look for the last 40 years, the price of electricity has remained relatively flat during that time period. The challenge we have is how can we reduce that CO2 emissions downward without having the price of electricity go upward? So that's the dual challenge we're trying to solve. And to put it in other terms, as engineers and economists, we like to do different graphs. But this is basically the wholesale price of electricity in cents per kilowatt hour. And this is emissions in terms of intensity. In terms of where the U.S. right now is, we do roughly about 0.65 metric tons of CO2 per megawatt hour that we produce. We're right here. And there's utilities all along this line across here. And where we want to be at that 83% is way over there. Trying to keep that price of electricity pretty much the same if we can, but reducing our emissions by 83%. Now, there's only one country in the world that is over in this territory, and that's France, because they are basically 85% nuclear provided electricity. I'm going to share two different models with you. One we call our Prism model, which is kind of a bottoms-up model. It's a technical assessment saying what's technically feasible to do. And then we did another run using some of the inputs from that into what we call our MERGE, which is a macroeconomic model, global model that looks on from the top down, what will this cost and what are the trade-offs that occur when you are adding cost into this equation. We use the Energy Information Agency base case as our starting point, and it's interesting to see this is how much the CO2 projections for the United States electricity sector. On the path forward, you see what it was projected to be in 2007, brought down a little bit in 2008, somewhat by the economy, somewhat by some new legislation on efficiency. Now this is the path in 2009. They just released their 2010, which we're going to work into an update of this study, but it's a little bit lower than the 2009, mostly driven by the economic impact in the country right now. But we put together what we call the Prism diagram, which is that pathway forward, using the technology options that we see that are technically feasible to go forward. And you can see why we call it the Prism, even though technically it's in the wrong color sequence. So anybody who gets the right color sequence, come on up here, we'll have a little prize for you maybe afterwards. But it was done by economists, not engineers, so they always tend to get the colors a little bit messed up. Well, let me walk through this, but the key thing is that by 2030, that 41% is on that path to get out to about that 80-some% reduction in 2050. And I'll walk through each of these. Different colors have different meanings. The blue is for efficiency, and we're looking at trying to reduce the load growth through efficiency in homes, businesses, and bringing it down from a little bit of right now is about a 1% per year average growth down to about 0.6% as our projection of what is technically feasible right now. And that ends up with about an 8% reduction in consumption out here at 2030. Now, we also tie into efficiency on the transmission and distribution system. Improved conductors, improved wiring designs, improved control can reduce the kilowatt hours that we lose in the T&D system by about 20%. And it's hard to see, but it's a very light teal color going through here. But every kilowatt hour you save reduces CO2. Renewable energy, a major component, which just flashed off and on again, is basically set at about 15% of generation out by 2030. And that's we use that number basically because that's a number that's in a lot of discussion around RPSs, renewable portfolio standards, a number most people feel that we can handle into the system. It may get as high as 20, I think, and be able to be handled. Right now we chose 15. And that's about 135 gigawatts of electricity from renewables. Right now we get roughly about 27, 28 gigawatts, principally from wind. That green slice is 4 times the amount of wind we have today, about 100 gigawatts. It includes about 20 gigawatts of biomass, biofuels, and about 15 gigawatts of solar, mostly concentrated in the Southwest. But it's a major expansion of renewables, and when you look at 15% across the entire country by 2030, is a fairly aggressive point. Nuclear power, we assume a couple things different than the EIA baseline. One, we don't assume any, there's no retirements. All the units that are moving up to their 40-year life get relicensed and continue on to a 60-year life. But then we add about 10 gigawatts of new builds by 2020 and another 64 in total by 2030. Now that 10 gigawatts that are on right now are the 4 major plants at the Southern Company, SCANA in Texas, and Calvert Cliffs up in Baltimore that are in the process of getting their license from the Nuclear Regulatory Commission. And those comprise, with some upgrades, about that 10 gigawatt number that I mentioned. On fossil efficiency, we look at both gas and coal and move the efficiency up for new units as quite effectively moving towards what we think are some of the gains that can be made in those technologies. We're having a little trouble here. But also then, one of the things that we're doing is that all fossil after 2020, both coal and large carbon and large gas, capture their CO2 emissions, 90% of the CO2 emissions. And that is kind of a new component into this. That means that any time you add a natural gas combined cycle plant, you also then have to capture the carbon off that plant. We didn't do it for the small intermediate peakers that supply the peak load in some cases, but for the larger plants. So essentially any fossil fuel you put in after 2020, you have to do carbon capture and storage. And the total of all these things, and I call it a full court press, because none of these are easy. You know, reducing the load by 8% is not an easy step. Bringing in 15% renewables, bringing in 64 gigawatts of nuclear, bringing all the new coal plants and large gas plants on with CCS after 2020. All these things are technically challenging. We think feasible, but challenging to do. But that's the type of numbers you're going to need if you're going to get on that pathway towards that 80% reduction. Now, there's other components when you decarbonize the electricity sector that allow you to decarbonize other parts of the economy. The first being electric transportation. I think almost everybody's up to speed on what's happening in electric vehicles. But as you decarbonize the electricity sector, when you plug in, you're using essentially nearly, much lower carbon electricity, eventually by 2050, nearly carbon-free electricity. So you can change the transportation sector, which is about 1/3 of the U.S. emissions, to a carbon-less approach by using electricity versus gasoline. The other is in what we call electrotechnologies. It's a technical term, but it's basically looking where you use either oil or natural gas in industrial and commercial processes and being able to electrify those also with decarbonized electricity. We only assume about 5% of the potential here. We took a very, very conservative slice here. But you can see these two numbers are almost as much as the efficiency component in reducing CO2 emissions. Now, if we take that situation, if we go through the prism and we get out to 2030, this is where we end up in the mix compared to EIA's, Energy Information Agency's, base forecast. We have a lot less coal in terms of standard coal, but beginning of introducing coal with CCS, natural gas, although in this case without CCS, nuclear expands by about 10 percentage points, and renewables go from 15% from 7%. This is the hydro component of 6%, which stays pretty much the same in either case. So when you combine hydro and other renewables, you're about 21% renewables out here at 2030. But then we took a case and said, well, this is one scenario of this. What happens, there's a lot of organizations, people saying, we don't want to use coal, we don't want to use nuclear going forward, we want to be able to just do this principally with renewables. So we took a scenario, which we call kind of the other end of the bookend study, and we limited the generation, in this case, of the portfolio going forward. And there's two things we did. We used what I showed you just earlier is called the full portfolio, where you have everything available, coal and gas, CCS, efficiency, nuclear. But on the limited portfolio, CCS is not available. Either it fails technically, economically, can't be sited, whatever. The other one is that nuclear generation does not expand. No new nuclear is permitted. And you have a few states in the United States right now, notably Wisconsin and California, that do have legal prohibitions on new nuclear in their state. So how do those two look? Well, this is the full portfolio, and I'll go into the generation mix in a minute. But you can see the full portfolio. This is the EIA baseline, and this is the limited portfolio, essentially this very similar baseline. One thing you notice that we call this a demand reduction. It's a combination of energy efficiency and what we call demand destruction. It's where, in one case, a demand reduction on the right, it's mostly energy efficiency. It gets out to almost about a 10 to 12% number compared to that 8% number I gave you earlier. In this case, it's even more. It gets up over in the 20, 25% number, mostly due to the price of electricity. And you also, in this case, we think begin to lose business and begin to lose industry because the price is so high. And you'll see that in a minute as I go forward. But in either case, aggressive energy efficiency is needed in either portfolio. This is how the two generation options differ. Now let me walk through these. The full portfolio, which is an extension of the Prism, only now using that economic approach. You basically see coal begins to fade out and fade out completely by 2040 on a nationwide basis. You get some coal plants, about maybe 20% of the existing plants are retrofitted, some of the newer ones for CCS. But after 2020, any new coal comes on with CCS. The other is nuclear grows here, as I explained, in terms of new nuclear units at 64 gigawatts. What you experience, though, is after 2030, some of the existing units start to hit 60 years of age. So they start to retire. So your retirements are kind of starting to get offset by your new units coming on. That's why you don't see this expand dramatically during this time period. You get a fair expansion of wind and biomass. Hydro stays pretty much the same. But one thing I want to point out, the CO2 emissions in this chart and this chart are identical out here in the year 2050. Now the limited portfolio is where you don't have carbon capture and storage available for either coal or gas, and nuclear is not allowed to deploy any further. What you see is that gas begins to really take over in terms of becoming the key generation mix. Your nuclear declines, and your wind, biomass, in this case even solar. Solar is fairly high priced, and all these economics are without any type of tax credit, incentive, production tax credit, so they're kind of a clean economic look at it. And what you see is that your renewable side ends up being about 50% of your generation. But an interesting thing we noticed as we went through this analysis, and if you look at this point right about here, and if you look at 2030 and going forward, you cannot add any more gas generation. And you ask why? Well, because you're starting to hit that carbon number coming down. And if you're trying to get to an 80-some% reduction, you can't use natural gas anymore to add generation. It has to come either from efficiency or from renewables. So you really start becoming constrained even on your major load capability of natural gas. Renewables are quite extensive in either portfolio. And as I mentioned, this gas situation is one that we're kind of concerned about. We recognize that gas, wind, and efficiency are going to be our next bridge between now and 2020, because you won't have new nuclear on board until after, late teens, early 2020, and in some cases, CCS probably won't be available till about 2020. So you need gas, wind, and efficiency in this next 10 years. But going out further than that, you do need to bring in new nuclear, carbon capture and storage, either for gas or for coal, in order to make that and hit that 83% line. That's the only way you can do it and keep the price of electricity affordable. Two different worlds when you look at this. This is the full portfolio at 2030, in which nuclear and your coal provide a good bit of your energy supply, very low carbon mix there, and you still have quite a bit of wind, biomass, hydro. This is the case in the limited, where you don't have CCS, so you lose, coal drops out, and you don't have nuclear growth. But then if you take this to 2050, watch what happens to the gas side on this side of the picture. You begin to have to back off gas generation in order to meet your carbon targets and greatly expand your renewable component. One of the questions we have, which we're doing a further study, can you operate the electric system with over 55% renewables? From a reliability side, we have some real doubts about that in terms of the intermittency of both wind and solar technologies. Biomass, fairly predictable, but the others are a lot more intermittent, and the need for storage is really critical if you end up on this path. Let's talk the price of CO2, because the price of CO2 then begins to drive the price of electricity. And you're starting at 2020, and this is without any type of price collar or restrictions or agricultural offsets. This is a pure, again, economic view on this. You're already at about $50 a ton for CO2. And in the full portfolio, where you have nuclear and you have CCS for both coal and gas, you go upwards to a little bit about $100 by 2040 and up to about $150. The limited portfolio has a much steeper rise in the price of CO2 because everybody's competing for that same natural gas. Both the transportation sector, the industrial sector, the commercial sector, and the electricity sector is competing for that natural gas. So what does it do to the price of electricity? Well, this is that wholesale price that I showed you before, just around 7 cents a kilowatt hour roughly that we have today. If you look at the full portfolio, your price stays relatively flat as you add, just in the next first 20 years. And as this time period goes on, as you're adding some CCS and nuclear and some renewables in here, it goes up. But it tends to then to levelize back off. You get about an 80% price increase between today's price, inflation adjusted, and going forward. That's still a significant increase. But if you look what happens on the limited portfolio, when you're moving principally to gas and renewables as providing your electricity, your price goes up even higher and you end up almost with 20-cent electricity, $200 per megawatt hour. Looking at in this other chart that I gave you, this is where we wanted to be in the goal. Try to keep the price level, reduce our intensity of CO2. These are how the two paths go. The full portfolio, you go from here to here, mostly in the same cases with wind and gas and efficiency. But then you're able to use carbon capture and storage and nuclear to keep your price fairly under control during this time period. What you hit in the limited portfolio, and this is where that wall was of when you can't use any more natural gas to emit, and you have to reduce load and go to pure renewables, all of a sudden your price goes quite a bit higher as you're turning towards a more expensive energy source. So these what we think is an area that is quite concerning us is this time period after 2030. We can get to 2030 with wind and natural gas. What our concern is what happens after 2030 to make that 83% target. We see two key challenges. One, on developing the technologies, continuing to develop solar, wind, carbon capture and storage to keep the options open in this area. The other is, don't accept a higher price of electricity. How can we innovate in order to be able to do things even better than we do them today to keep that price of electricity as low as possible. It's a major economic growth engine for the United States. And we're concerned that even that 80% increase can affect the growth possibilities for the United States. Our goal is to try and keep it under that number as much as possible while still decarbonizing the electric sector. So in summary, our messages come down to the point that you need all these options. You need efficiency, you need efficiency in the power grid, you need renewable energy, nuclear, fossil, you need it with CCS. And the decisions that we make over the next 10 years of either keeping these things in the mix and developing them as rapidly as we can and efficiently as we can, or knocking them some out of the mix, will depend on what we'll have as a generation option in 2050. So the next 10 years in terms of technology development and public policy are extremely important. Now the details are all on this. If you want to write that number down, that 7-digit number, it is not the lottery code for Powerball. You can try it, but see what you get. But if you go on EPRI.com, and there's a search number up there, you type that number in, you can access this full report and download it. There are some small, what I call Reader's Digest versions that Commissioner Honorable is going to hold up here that are available. We'll have on some of the tables as we break up here. But you can get the full report and all the details on it if you're interested on EPRI.com. So thank you for your time and attention. I appreciate the opportunity to be here, Commissioner, and happy to stay as long as I can for questions.
Thank you for that. And if you do have questions, please raise your hand. We'll get a microphone to you right here.
I was just curious on the limited portfolio, why remove the carbon capture system from that scenario?
Basically, when we're saying on the limited portfolio, we're saying carbon capture and storage is not available. And it could come from any of 3 reasons. One, we're working to bring, making it technically feasible. We think it's doable. Economically, and that it's price effective to do. But the last gets into storing CO2 in the deep underground aquifers and the environmental permitting challenge of that. If any one of those 3 would not go through, and I think it's more the siting side that's going to be the biggest challenge here in the United States. That's why we took that out of that. That could not be an option going forward if that occurs.
Ready?
On your chart where it was metric tons of CO2, and we're moving from 0.65 over to 0.1, and France is there now because of the high nuclear generating capacity. Did you look at some scenarios, because it seemed to me you were fairly conservative in the nuclear option. Did you look at some scenarios, is that possible to increase that, and what impact would that have on that chart?
Yeah, the number we looked at in the nuclear side, that's 64 gigawatts that we looked at, could be larger. But one of the things I think that we actually put a little bit of a limit on the number of new nuclear plants that you can build per year from what we view as kind of a practicality in terms of getting the forgings that you need for reactor heads, nuclear fuel supply, things like that. So we kind of put a growth limit on that. It's interesting, that's roughly 64 gigawatts that happens from 2030 out to 2050. In terms of 2020 to 2030, there's 64 gigawatts. So that's 50 gigawatts in 10 years. We built 50 gigawatts in this country the 10 years prior to the 3 Mile Island accident, and 50 gigawatts in the 10 years after the 3 Mile Island accident. So it's a number that we went back to and kind of said it's a practical number of the pace. If you let the model run, because nuclear comes out basically as the lowest cost energy provider, it would take everything. But we put a cap on that to hold that down, making it what we call realistic in that case.
And if you
Good question.
Introduce yourself before you ask the next question. Not just you, but everybody. Just introduce yourself.
I'm Michael Fess. I read that the Iceland volcano just negated all the savings for the last 2 or 3 years. Is that true?
I've asked that question of a couple experts in the climate science area, and they said no. They said it actually does somewhat of the opposite. it throws up a lot of particles, and especially sulfate particles, into the upper atmosphere, which is like a cloud which basically reflects sunlight and actually cools the Earth in that situation. And the amount of CO2 out of that volcano basically is negligible in terms of the total global scheme. So it's actually the opposite effect in that case.
Anyone else? All right.
My name is Mike Abel. The mood in Congress right now, when whatever system they put in place, when they'll get a tax or they'll get money somehow, do the congressmen tend to want to pick the technologies based on their interests, or are they just going to let the marketplace take it, or which way are they leaning?
I would say Congress has changed, and I won't put it just with our work, but we've shared this study, which is the basic message for us is keep as many options open as possible going forward to keep the price down. I would say 5 years ago, there were a lot of technology pickers. We ought to do this, we ought to do that, we ought to do this. And that has changed quite a bit. They recognize the need to keep all the options in there and be able to manage it under basically a cap and trade program that you set the targets and then let the market to decide the technology and drive the technology development. So I would have to say, and I spend probably a week, a month up in Washington, I would say there's been a sea change in that 5-year period from set the targets, let the industry and government, or the industry work on making that, versus being very prescriptive. So I think we helped educate that process quite a bit.
Hi, I'm Bruce Streisner. I'm an engineering undergraduate at UALR, and you said that going with the limited portfolio, we'd end up with about 55% of our energy generated from renewable sources. What sort of engineering obstacles what measures would be taken to enable the grid to handle the intermittent nature of those kind of renewable energy, or that kind of renewable, those kinds of, you know what I mean. And
Good question, I got you.
if you could just talk a little bit more about that, I'd really appreciate it.
Yeah, one of the things that's, if you look at that slide, it ends up in the limited portfolio about 50% renewables. And it's a mix of some biomass, and biomass is fairly predictable. You can operate it like many other plants. You can control the fuel input, and you know what kind of output you're going to get at what time of the day. One of the things that we see with wind and also with solar is the intermittency issue. Especially wind has a situation that is very concentrated in the core Midwest, upper Midwest especially, where there basically needs to have a lot of transmission. We have about 10 years of building transmission into the Midwest in order to capture that wind. But even if you capture that wind and include the price of that transmission, which can be very expensive, what you have is that wind at some times of the year doesn't blow. And what you're having a situation, especially when during hot summer days, you go out in many wind turbine areas, nothing's turning. The time when you need electricity the most. One of the key technology issues is, can we develop a storage capability either through compressed air underground, battery technologies, et cetera, in order to be able to handle that and store that. The scale of being able to do that right now and the technology development, we say might be solved, but we don't see it contributing a lot in the next 20 to 30 years. And we might be wrong on that. That's one of the wild cards, as I would put in this analysis. If we're able to get low-cost energy storage, it can transform this quite a bit. That might come as you get more electric vehicles. The battery development might get better and better and better. But right now, you want to try and do your planning and what you can have a certain degree of certainty on. And the wind issue right now we see is one that the intermittency is very valuable to take it when you can, but you need backup almost equal to its full capacity in order to provide the reliability. That gets into that third leg of reliability, affordability, and reducing carbon. That's around the reliability issue principally. Good question.
Wally?
Wally Nixon with the Arkansas Commission. You talked about this roughly 7 cent per kilowatt hour average price. A lot of places are higher than that now, and of course we're lower here in Arkansas. What I'm wondering is there also part of the analysis any look at what bills are as opposed to rates. What the average bill is, and that ties into the consumption levels and
Yeah.
forecasts and all of that.
Yeah, we don't have it specifically laid out in that scenario, but one of the things about, if you look at that efficiency component, that if, in almost every case we showed here, we see the price going up somewhat. And our efforts are trying to minimize that. So can you do through efficiency, be able to, what I call mitigate people's bills, that maybe the price goes up somewhat by efficiency can help, control that. We haven't worked that in the study. That's an interesting thing that I think we need to add in. Where we're staying on is that the basic technology we want to choose should support as low a cost as we can to keep electricity affordable. But it's an area I think we're going to do more work on.
Bill in the back, Martha.
I'm Martha Jane Murray with the Clinton Climate Initiative, and I have an interest particularly in the energy efficiency side. I have a concern that since that's, sort of taken for granted that that's going to be our biggest impact in the next 10 to 20 years, that there's sort of a complacency that that's going to come along with the technology. We have incentives, but we don't have a price on carbon to really ensure that we get there through energy efficiency. Do you have a specific roadmap on the mix of that to achieve that 1% reduction each year in terms of residential, commercial, industrial?
Yeah, what we're working on, and it's a great question because efficiency is going to be extremely important over the next 10 to 15 years in terms of mitigating the growth that we can, until we get other technologies available. We're working quite actively. I spent some time in Washington last week with a number of the energy efficiency organizations and the Department of Energy in terms of collaboratively bringing together a roadmap of what codes and standards are needed for appliances, new buildings, what codes are needed for retrofits of buildings, and also what kind of technologies can you do to improve the efficiency of water heating, air conditioning, heat pumps, things like that. So the three, it's about 7 organizations in total, are working to try and build that roadmap. Our job is to try and develop the next generation of what we call hyper-efficient technologies. But codes and standards play a huge part in this, and that's basically government-driven. So DOE is working on that, working down through the states. So I won't say there's one roadmap I can pick up and show you, but we all have the confidence that we can make that 8% reduction by 2030. But we need to put those things in place.
Right here.
Hi, Eddie Moore, also with the Arkansas Commission. What's the assumption about the per capita usage of kilowatt hours in that modeling? Does it continue to go up or flatten out or go down? Or?
On a per capita basis, I don't have that right on top of my finger, but what you're looking at is eventually you're getting, in that first part, we're saying about an 8% reduction. I don't know if that time frame would grow by 8%. So I think it gets fairly flat, is what you're looking at. And what we're seeing is, we think over time that you'll get to fairly flat growth rates when you start getting out beyond 2030, 2040. The one we show here is like 0.6. And we think that might even drop lower as you go further out. But I don't have an exact per capita number.
Has the EPRI fusion prototype been figured into any of your projections?
Not in this time frame. And it was interesting. I had an opportunity to go up to what's called the National Ignition Facility up at Lawrence Livermore National Labs, where they are working on fusion. Basically, it's called laser-induced fusion. They have a view, and very, very smart people working on this, of trying to get fusion energy into the mix in the latter half of this century. I don't think we'll see anything by 2050, but if you ever have, they do not public tours, but group tours, like at commissioners or something like that. It's a fascinating facility where they take 196 laser beams about the size of this, concentrate it down, and hit a nuclear particle no bigger than my fingernail. And that's how they induce that fusion. And they're ready, they've been going through startups and that, and it's a fascinating facility. Anybody from the commission or the school, if you have a chance, it's at Lawrence Livermore National Lab, National Ignition Facility. It would really, kind of open your mind, I think, to the potential of fusion, but I would say view it as the latter half of this century at the earliest.
Right here, Bill.
Hi, Evan Brown, the Arkansas Energy Office. It looks so easy when you see it on the charts, but what you're really talking about is a paradigm shift that won't come easily. And you mentioned that we need to make a decision in the next 10 years. It seems like more than a decision is needed. We need to make a commitment and then move on it, because otherwise our history is that we have to wait till things crash before we can fix them. Right. And you're talking about fixing them before they crash.
Very good point. You know, what we see is that you need initially some price on carbon. Whatever that happens to be, if the Kerry-Lieberman is the price or other approaches coming through. But that drives a couple of things. It drives behavior for efficiency because it affects the price of electricity. It also drives the technology development. You won't see carbon capture and storage unless there's a price on carbon. You wouldn't do it unless someone does a legislative of a mandating it in a different way. So that legislation, I think, is the key first step, both at the federal level, but then working at the state level. How do you work on building codes and standards, things like that, in order to be able to, mitigate the growth rate somewhat, and then develop the licensing and siting of new nuclear is basically a state level initiative. I call it a full court press. Every color I showed in that prism is not an easy thing to do. And if you lose one of them, it puts so much pressure on one of the other ones. So, it's every slice in there is hard to do, and yet we think it's doable. We just need to get on with it.
Hi, Jay Caspery with Southwest Power Pool. I'd like for you to explain how you think the smart grid first is defined and how it plays into enabling these changes for the future.
Okay. And that's a complex question, because the word smart grid, as simple as it is a very complex subject. I'll put smart grid into really three different components. One would be on the transmission side. The ability to be able to have more capacity, better sensors, better control of transmission energy flow, electricity flow, so that we can be able to bring in wind energy, be able to adapt to swings and loads on wind or solar that occur, and that transmission has to have that capability is one part of the smart grid. The other part, I would say, is the distribution system. Reducing some of the losses in that system, being able to give price signals to consumers in terms of what their energy costs are, but also be able to communicate and take in power from rooftops, photovoltaic, things like that. That changes the distribution system, which is now a one-way street, designed as a one-way street, and you're turning it into a two-way street. That has to change in the grid. And the last part I see is inside the home, where you start seeing appliances that have sensors in them, thermostats that have sensors, so you're tying communications with the electric utility industry in order to give not only price signals, we call it prices to devices, so that you send a price to a thermostat or to a dishwasher or to something else, a refrigerator, and that device responds in some predetermined way. You don't want to give prices to people. They should know it, but if you want to optimize the system, you're much better off going to the device and being able to optimize that. So I see those three parts are all needed in the smart grid to make it successful going forward.
The carbon capture technology, I think it's struggled here in the last few years. What's the status at this point?
Yeah, right now we're doing a demonstration. The scale right now is 20 megawatts, which is not large. It's at American Electric Power, AEP's Mountaineer Power Plant in Ohio. That's about a 1,000 megawatt power plant, to give you a scale. We're taking off a 20 megawatt slipstream and then using a technology called chilled ammonia. It strips the CO2 out of the flue gas, concentrates it, and on that site it's actually being injected right under the power plant about 8,000 feet down in a geological formation. We're going to be doing the same thing with Southern Company in a plant just south of Mobile, Alabama, starting next year. Those are the two largest in the United States. Right now, what we need is to move that. We started last 4 years with a plant in Wisconsin at 2 megawatts. So we went from 2 to 20. And if these 20 megawatt plants work well, the next step is take it to 200. And then if you hit the 200 level, we think that can make it successful. It can be commercially deployed beyond that point. Some of the manufacturers, Alstom, who is one of the major ones and has the AEP installation, are saying they think it could be available as early as 2015. We've been saying commercially available about 2020. But what we need is about a dozen large couple hundred megawatt installations to be able to test the capture, and then also do what I would call as a good test on the stress test of the geological formations. We need to do both within the next 10 years so that 2020, someone can call up, order a power plant, and have it with 90% CO2 capture. So there's a lot to do in 10 years on that, a lot of research to be done yet.
Yes, sir.
I'm John Allen with the Science and Technology Authority. Regardless of the option chosen and the path forward, does the electric power industry have the engineering talent to pull it off?
You know, we've been facing a lot of discussion around the change of, what I call changing of the guard, where the average age in the power industry has been up in the 50s and a lot of people are retiring in the next 5 years. I think that's facing a lot of technical areas. I worried about it a lot up to about 2 years ago. And it's interesting, we're starting to see a lot of new graduates coming out of the schools interested of getting into the electricity area and the energy area. 10 years ago, someone coming out of a university, EE program wanted to go to Microsoft or Cisco or someplace like that. We're seeing people wanting to come to EPRI and some of the utilities because they can work on wind, solar, carbon capture and storage, new nuclear. It's a different paradigm. I'm a lot more comfortable that we're starting to see that transition, that we're seeing a lot of new graduates coming out that may replace that aging workforce for the electricity sector. The key is on technology transfer and the lessons learned. But it's interesting, you take a new 23-year-old engineer and put them out with a 55, 60-year-old engineer, how they work is quite different. The 22-year-old has, the PDAs, how they communicate, how they work, and they're looking for a different paradigm than what the system is running on right now, I would think. So I'm fairly confident we can handle that issue. It's not one that can be ignored, but I'm a lot more comfortable than I was 2 years ago. It's interesting in EPRI, the reason I say that, at EPRI, 1/3 of our staff, and we've been bringing new staff in as we've been doing a lot of new work, 1/3 of our staff has less than 2 years. Some of them may come in second careers and stuff like that, but we have this young, new, emerging talent coming into the organization in their 20s and 30s, and some, even in their low 40s, which I think has really brought a lot of great ideas in. I think that's kind of renewed my confidence personally.
We have time for one more.
Based on Chris Callahan with NGI, based on today's technology and regulations or non-regulations and funding, which of the goals, how to reduce CO2 footprint, keep electricity affordable, which of those is the cheapest, quickest, and easiest to implement, assuming that there is none, and how is the government or how are the influencers positioning the government to implement those things first that will save the most quickest?
Well, I think right now most people would agree that the cheapest and easiest is energy efficiency, although it's not happening at quite the level we think it should happen. And I think that's somewhat of just consumer behavior, social change, things like that. But if you can build a new building that's going up today and design it right, you can substantially cut the energy needs for that building, and that building's there for another 50 plus years. So that is probably, no doubt, the easiest and cheapest, especially on new construction. It's a little bit harder on retrofit. I think the other thing that it's important, nuclear I see as a deployment challenge. There's a lot of cost in nuclear, but once it gets on board, it produces very, very low-cost electricity. So getting that deployment challenge is mostly a licensing issue, siting issue, and I think that's also a very important one to get into the mix in terms of providing low-cost, carbon-free electricity. But back to your question, I think energy efficiency is the first to do.